Welcome to this online training about creating a system design with Platform Designer. My name is Steve. This training is available for desktop viewing, as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the link provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you by the end of this two-part training, you will know how to use the Platform Designer user interface to create a system design for implementation in an Intel FPGA device. Along with this, you will see how Platform Designer fits into the Intel Quartus Prime software design flow as another method of design entry. Continuing from Part 1, there are a few additional things to be aware of when connecting basics of its use when starting system connections between all interface types. You'll learn how to finish building a connection method and incorporate it into an Intel Quartus Prime software project. Non-exported interfaces Part 1 will be flagged with warning or error messages, depending on the type of interface. It's okay if there are blue warning messages, but any red errors must be fixed in order to generate the system. To finish up this connections discussion, let's look at some details regarding specific types of connections, namely clocks, resets, and conduits. As mentioned earlier, all components include at least one clock interface because all transactions between components are synchronous. To simplify the process of setting up clocks for all components in the system, you can use a clock source component or a clock bridge. All new .qsys files created in the Standard Edition include a clock source component, while new systems in the Pro Edition include a clock bridge. Both components operate identically, and you can remove the component if you don't want to use it. The clock source or clock bridge component is essentially a clock interface aggregator. It is used to distribute a single external clock that enters the system to the clock interfaces of other components in the system. Without one of these components, the clock input interfaces of all components in the system would need to be exported individually and connected to the external clock outside the system. Each clock bridge or clock source component has a clock input interface and a clock output interface. The clock input is exported out of the system by default to connect to an external clock. You can connect the clock input interface to external sources like a clock oscillator device on your board or an FPGA PLL that resides outside the system. The clock output interface is then connected to the clock input interfaces of all the components that use this clock. Use any of the connection strategies discussed to make or break the connections. The clock aggregator components have only a few parameter settings. However, one parameter specifies the input clock frequency. This is used for clock constraints to help close timing in the system design. You can add additional clock bridge or clock source components if your system uses multiple incoming clocks. If a component has a unique, non-shared clock interface that connects directly to an external clock source, then just export that interface directly. One of these components is not needed. Along with these clocking components, another way to easily make clock connections is to use the clock column in the System View or System Contents tab. For any clock input interfaces in the system, click in the clock column as shown to get a drop-down list of clock output interfaces in the system. Select which clock you want to use as the source for this interface. A connection is made to the clock source and indicated with a new black dot in the Connections column. To manage the different clock domains in your system, use clock domain filtering along with the Clock Domains tab, accessible from the View menu. This tab displays clock domains as hierarchical regions with each component and that component's interfaces in that clock region displayed underneath. By selecting a particular clock domain or multiple clock domains in the tab, the System View or System Contents tab can be filtered, displaying only the components being clocked by the selected domains. When selecting a domain, the System View or System Contents tab also displays colors to show which interfaces belong to which clock domains. You can further filter the System View or System Contents tab to display only the component interfaces in the domain, in case a single component has interfaces in multiple domains, like the PLL in the example shown here. If there are multiple clock domains in your system, and you make a connection between two components clocked by different domains, the Clock Domains tab also shows the location of any clock crossing logic being implemented. Platform Designer automatically adds clock crossing adapter logic to the interconnect where needed. Red dots in the System View or System Contents tab indicate where the tool will add an adapter. When hovering over these dots, tooltips provide details about why the adapter is required. You can choose to allow the adapter to be inserted, or you can adjust the design to avoid its creation. In the example shown here, the reset interface of the push-button switches component is synchronous to a clock that is different from the clock used for the source of the reset. The tooltip explains this difference, and the different colors show how the components are in different clock domains. Note that this may be okay for the design, since the whole idea behind Platform Designer is to automatically add logic to the interconnect to fix issues like this. However, if timing issues are found in the clock domain crossing, using the same clock for both the components may fix the issue. We'll take a closer look at reset interfaces next. Reset interfaces in Platform Designer are separate from clock interfaces, though they, like other standard interfaces, are always associated with a particular clock domain. External resets can enter the system just like clocks, optionally through a reset bridge in the Pro Edition or a clock source component in the Standard Edition. When specifying the parameters for these components, you can explicitly control the synchronization of the reset with respect to the clock signal of that component. Resets can also be generated by other components in the system. They can provide reset control to the system through a reset output interface. For connecting resets, you can use one of two methods. The simpler method is to use a global reset. Simply select the Create Global Reset Network option from the System menu. With this option, Platform Designer automatically ORs all reset output interfaces, synchronizes them to each clock domain, and connects them to all reset input interfaces. The exception to this would be any reset input interface that has been exported, such as the reset input interface of a reset bridge or clock source component. In most cases, you would use this option if there is only one reset domain in the system, instead of ORing all the reset domains together. You can also choose to make specific connections between certain reset output and input interfaces, giving you complete control over resetting individual components in the system. With this configuration, a given component can be reset by a particular subset of all the reset sources in the system. If this method is used, care must be taken to avoid reset loops or reset situations that can cause system lockup, such as resetting a component with an agent interface in the middle of a transaction. If you have multiple external resets entering the system through multiple reset bridge or clock source components, you can use a reset controller or reset sequencer to manage them. See the Intel Quartus Prime Platform Designer User Guide for details on these components. In the example shown here, resets are being hooked up manually. The reset input interface of the clock source component is exported to connect to an external reset signal. The reset output interface of the clock source component is connected to the reset input interfaces of components in the rest of the system. The reset bridge component in the Pro Edition functions the same way. For all reset interfaces as well as other non-clock interfaces, the clock column indicates which clock interface on a component is the clock input interface used for synchronization of that interface. For example, the highlighted button debounce in reset input interface is synchronous to the clock input interface named clock on the reset debounce component. Similar to clock domain filtering and the Clock Domains tab, you can filter on reset domains and open the Reset Domains tab from the View menu to see which components and interfaces are in which reset domains. This is particularly helpful if you have made your own specific reset connections instead of using the global reset option. Again, you can enable further filtering to display only reset interfaces instead of all interfaces for each component. Similar to viewing clock crossing adapters, you can see where reset synchronizers or other related logic have been inserted in the system by selecting a reset domain from the Reset Domains tab. Again, red dots on the System View or System Contents tab indicate their locations, and tooltips indicate why an adapter is required. The three situations listed are the reasons why an adapter will be inserted. As with clock domain crossings, you can leave the adapter in place or adjust the design to avoid the need for it. Sometimes the adapter cannot be avoided. In the example shown here, multiple components can send a reset to the Reset Debounce custom component. As such, an adapter is needed to OR the two reset sources so either can reset the button debounce component. The final type of interfaces to be aware of are conduits. Conduit interfaces in Platform Designer represent any non-standard interface types or signal groups. They can contain any arbitrary signal or collection of signals. Conduits appear right along with standard interfaces for a component in the System View or System Contents tab. While conduits can be connected to other conduits with the same signals using two connection dots as shown, they are usually exported out of the system to be connected externally. Conduits are used, for example, for things like I/O signals that connect to LEDs or for high-speed transceiver I/O. You can view the individual signals that make up a conduit by expanding the conduit in the Hierarchy tab or by selecting Show Signals in the Block Symbol tab. For all off-the-shelf components in the IP catalog, conduits and their signals are already defined. If you create custom components, you must specify what signals make up the conduit. See the follow-up online training, Custom IP Development using Avalon and ARM AMBA AXI interfaces, linked at the end of this training. With all the connections established, let's look at setting up address maps for memory-mapped interfaces. The final item that must be configured before reviewing and generating a system is the memory-mapped addressing for any component interfaces where it is required. You define the addressing for the memory-mapped or control plane portion of your system. Platform Designer supports up to 64-bit addressing. Each host interface has its own unique address map it uses to access the agents to which it is connected. The address span of a host interface is the collection of the address spans of all its connected agent interfaces. The address span of each agent interface is determined by the lowest or base address assigned to it within the connected host's address space and the size of the component's addressable register map for the interface, defined by the component itself. As connections between host and agent interfaces are made, Platform Designer automatically populates the base and end address of each agent interface. To change the assigned address for a particular agent interface within the address map of the connected host, double-click the agent's base address and type in a new address. This is defining an offset from address 0 of the connected host, where the host will start accessing this component. Customizing the base address can be done to simplify decoding logic, to enable the use of some pre-written software or hardware logic, or to resolve agent interface address conflicts. The end address column cannot be edited, since the address span of a component is based on the design of the component itself. In the example shown here, 5 components and the exported interfaces of 3 subsystems are connected to the host interface named State Machine. The address map for this host starts at 1030 and goes up to 9FFF. If there are any gaps in the address map, accesses to them are automatically handled by the interconnect. If multiple host interfaces connect to the same agent interface, the host port's address maps converge, as the agent ports will, by default, be assigned the same address for each host port. Agent address spans cannot overlap the address spans of other agents connected to the same host. If you don't require specific addressing, you can let Platform Designer auto-assign non-overlapping addresses. To do this, simply select Assign Base Addresses from the System menu. If you want to prevent any manually assigned addresses from being changed due to using the auto-assignment option, click the indicated lock icon. Besides the base and end address columns on the System View or System Contents tab, you can use the more detailed Address Map tab. The Address Map tab contains a complete table of all memory-mapped device addresses, making it a little easier to configure the address mappings and address spans in the system. On this tab, each column represents a memory-mapped host interface, and each row represents an agent. If a particular agent is connected to a host, the cell representing their intersection is filled with the agent's address span as that host sees it. By default, each agent is assigned the same address range for all hosts that connect to it. Just like on the System View or System Contents tab, you can double-click a cell and edit the address for an agent's connection to a host. Entering a base address into an empty cell on the Address Map tab is a handy way of making a host-agent connection and setting a base address in one step. If an agent is connected to multiple host interfaces, indicated by multiple address ranges in a row of the table, the agent address is only changed for the host in whose column the cell is located. Thus, an agent interface can be represented by different address spans for different hosts. In the example shown here, the in-agent interface on the LED FIFO component is accessed by 3 different hosts. For 2 of those hosts, the agent is accessed at address 0, while for the third host, the agent is accessed at address 1050. If an agent is accessed at 2 or more different addresses because of multiple host connections, mixed appears in the base and end address columns of the System View or System Contents tab, requiring the use of the Address Map tab to edit the addresses. Platform Designer in the Pro Edition features an enhanced Address Map tab. With it, you can get details on the address space for each host individually. The list on the left displays the system and all host interfaces in the system in a hierarchical view. Selecting the entire system option at the top of the list provides the same address map view just discussed. For the enhanced view, select an individual host from the list. The list of host interfaces can be filtered using the search field just above the list. When an individual host is selected, a graphical view of the full address space of the host is displayed, along with a list of connected and unconnected agents. Base addresses set on the System View tab are displayed. Fill in a base address for an unconnected agent to make a new connection, yet another way to make connections and set addresses in one step. The graphical view allows you to visualize the address map, displaying colored areas that approximate the size of the address span for a particular agent. Click and drag from left to right to zoom in. Drag from right to left to zoom out. Both the table and the graphical view will highlight any address space overlaps, making them easy to fix. Once all components are added to the system and connected together, you'll want to review the connections you've made and the system you've built. At any time during the process of building a Platform Designer system, use the various tabs discussed so far, like the System View or System Contents and Clock or Reset Domains tabs, to review and verify your work. There are also additional tabs available to help with this process. As before, all of these tabs are accessible from the View menu. We've already mentioned the Parameters tab. On the Parameters tab, you can review and edit the parameter values and options selected when a component was added to the system, just like in the Components Parameter Editor. Just select a component in any of the other tabs and go to the Parameters tab. If you need to modify any parameters, you can do it directly in the Parameters tab without reopening the Parameter Editor. The Schematic tab provides a schematic view of the system. Often, visualizing the system as a block diagram can aid in understanding the flow of data or how control logic fans out in the system. filter the schematic by excluding instances or types from the display to focus on only a part of the schematic. You can also make or break interface connections directly in the Schematic tab. A bird's eye view of the entire system makes it easy to navigate around larger, more complex designs. The Block Symbol tab displays a block symbol diagram of a selected item, whether it's an individual component or the entire system. If the entire system is selected, the external connections to the system are highlighted, similar to the view in the Schematic tab. All interfaces exported out of the system appear on the symbol. You can see the individual signals that make up each interface by enabling the Show Signals option in the tab. The Hierarchy tab lets you easily review system connection details, including the results of settings chosen in the System View or System Contents tab, in a hierarchical format similar to the Project Navigator found in the Intel Quartus Prime software. In this tab, you can view the entire system, the components that make up the system, any exported interfaces, the interfaces for each component, the signals that make up each interface, as well as all the connections between component interfaces. For system editing, the System View or System Contents tab includes a toolbar that allows you to remove or edit components in the system, as well as change component ordering. Rearranging the order of components in the system is primarily for cosmetic or readability reasons. For example, you can group related system components, such as components with streaming interfaces or components with host or agent interfaces connected together. Changing component order does not change any component interface connections, nor does it change the addressing of any memory-mapped agents. There is also an option to quickly create a new empty subsystem and make it part of the current system. Normally, you'd have to manually create a new .qsys file and then add the new subsystem to the current system from the IP catalog. With the New Subsystem button in the toolbar, this is done with one click. You can immediately start building the subsystem and connect it to the main system. Additional controls in the System View or System Contents tab help when working with subsystems. Instead of opening a separate instance of Platform Designer, or manually opening and editing the .qsys file for a subsystem design, which would close the current system, select the subsystem already added to the design and click the Drill into Subsystem button. This is essentially the same as opening the .qsys file, but you can immediately return to a higher level system using the indicated up arrow options. Though not specifically used just for subsystems, the zoom buttons in this toolbar let you zoom into the individual signals that make up interfaces, either the interfaces in the current .qsys file or the exported interfaces of a subsystem. Zooming in displays a list view of the individual signals. As mentioned earlier, use the Block Symbol tab to see individual interface signals graphically. We saw earlier that you can filter the System View or System Contents tab by selecting clocks and resets in the Clock and Reset Domains tabs. For more filtering options, you can choose from a number of included system filters or create a custom filter in the Filters dialog box. Select one of the available filters from the list at the bottom of the System View or System Contents tab, right-click a component for a filter submenu, or open the Filters dialog box from the toolbar. With the built-in filters, you can filter components and connections based on things like interface type and component connections. However, with the Filters dialog box, you can even filter based on component name. The default filter view is to show all components and interfaces. In the Filters dialog box, click the New button to create custom filters and store them for future use. Give your new filter a name and define the criteria. The criteria can be based on things like component name, interface type, or what objects are connected to. The Pro Edition features live filtering of the System View tab with a dedicated Filter tab. Instead of selecting a predefined filter or creating a custom filter and then applying it to the system, you can simply select individual items or control-click multiple items that you want to appear in the System View. In this way, you can focus the view on exactly what you want to review or edit. The Filter tab even has its own filtering options. Choose whether you want to view exported interfaces and what system items you want to filter on. All systems consist of 4 basic items, represented by the small icons in the Filter tab: subsystems, components, interfaces, and individual wires. Options at the top of the Filter tab and System view allow you to expand the selected filtering to components or interfaces outside of the items you've selected to see those additional connections without adjusting the current filter. This makes it much easier to make correct connections between component interfaces in a hierarchical system design. Instead of having to manually export an interface from a subsystem and then switching the view to connect it to another location in the hierarchy, you can view both the source and destination of the connection you want to make simultaneously, even if they are at completely different levels of the system hierarchy. Then, when the connection is made between different hierarchy levels, the subsystem interface is automatically exported, further simplifying the process. The final step is to generate the HDL code for the system. With the system built and reviewed, you are just about ready to generate the system with its custom interconnect. In the Platform Designer Standard Edition, use the Device Family and Interconnect Requirements tabs to specify system-level settings that will be used by the tool when generating the system. On the Device Family tab, make sure your target device family and part number are set correctly. If the system was created from an open Intel Quartus Prime project, which is a requirement for Platform Designer in the Intel Quartus Prime Pro Edition software, this information should already be set correctly. You can change the target family and device if you want to optimize the generated output for a different device. Note that the exact part number is not needed to build a system, but it is still recommended to have it set correctly. In the Pro Edition, the device settings are located in the separate System Settings dialog found in the Tools menu. On the Interconnect Requirements tab, choose options that affect the implementation of the interconnect. Specify the maximum number of pipeline stages automatically inserted into the interconnect to trade off between system performance and cycles of latency for performing memory map transactions. You can also select how you want any automatically generated clock domain crossing logic to be implemented, as handshake logic, as FIFOs, or let Platform Designer choose the implementation automatically. With Auto, a FIFO is chosen for links that support bursting, and handshake logic is used for all others. The Interconnect Requirements tab also includes a number of other requirements you can add and customize based on how you want to set up and operate your system. See the Platform Designer user guide for details on all the options available. In the Pro Edition, the Interconnect Requirements tab has been replaced with the Domains tab. This lets you choose custom interconnect requirements for each memory-mapped domain instead of for the entire interconnect. Select a domain from the list and set options for that domain. The Pro Edition includes some options similar to the Standard Edition, but additional options are available for the advanced devices only supported in Pro. For example, it is recommended to use synchronous resets as much as possible when designing for a HyperFlex device, such as Intel Stratix 10 and Intel Agilex devices, since the hyperregisters found in these devices' routing fabric do not support asynchronous resets. Platform Designer defaults to always use synchronous resets in the interconnect for these devices. As in the Standard Edition, add custom requirements for interfaces in a particular domain, using the Interface tab and additional low-level requirements on the Post-Adaptation tab. Again, see the Platform Designer user guide for details. At the bottom of the default Platform Designer user interface is the Messages tab. This tab lists all informational, warning, and error messages, organized by message type. Listed messages are based on the options you've selected and the connections you've made or not made in the system. The Messages tab is live, so messages may appear as soon as you perform an action in another tab, such as simply adding a new component to the system. As such, don't worry if you suddenly see a bunch of error messages appear. The errors will go away as you make connections and finish building the system. Double-click a message to highlight the item in the system that the message is referring to. Error messages in red must be reviewed and fixed before the system can be generated. While the system can be successfully generated with warnings, it's a good idea to review the blue warning messages to make sure they will not cause any issues in your completed design. Once you've finished your system design, you need to generate the HDL code that describes the system's components, interface connections, and interconnect. Generation creates all the files needed to synthesize or simulate the system, as well as additional support files that may be needed for things like software development for an embedded processor. It can be performed either manually in Platform Designer or automatically during compilation of the main Intel Quartus Prime project. System generation is much faster than compilation, so manual generation lets you fix issues with the system without interrupting a potentially lengthy compilation. Once the system is set up properly, you can let it be regenerated as needed automatically during compilation. To perform a manual generation, select Generate HDL from the Generate menu or click Generate HDL at the bottom of the Platform Designer window. Select the files you want Platform Designer to generate based on whether you plan to synthesize or simulate the system. Platform Designer can generate simulation model files and scripts for simulation, synthesis optimized files, as well as a symbol file for adding the system to a schematic design. For both simulation and synthesis, choose the HDL language for the output files. In the Standard Edition, the directory path where the generated files will be located can also be adjusted, while this is a fixed location in Pro. Note that in both Standard and Pro, this defaults to a new directory in the Intel Quartus Prime project directory that matches the name of the system. Also note that only the base location for the generated output files can be selected. The subdirectories where all generated files are stored are derived from that base location. Click Generate to generate the system. If the system will not be at the top level of your Intel Quartus Prime project, you will instantiate it as a submodule in another design file. To simplify this process, Platform Designer provides an instantiation template. The template includes all the individual signals in all the system's exported interfaces. Each signal is prefixed with the name that was specified in the Export column of the System View or System Contents tab. To create this template without generating the system, from the Generate menu, select Show Instantiation Template. Choose whether the template should be in Verilog or VHDL, and copy the code into your design file. Edit the port mapping sections in the template to connect the system to the rest of your design. So those are the main steps for creating a system design in Platform Designer. To review, select the components you want in your system from the IP catalog and configure them using each component's parameter editor. Use the Platform Designer user interface to connect or export interfaces. Set up host address maps where needed. Review the connections you've made to make sure they are valid and match the design's intended behavior and functionality. And finally, generate Verilog or VHDL files to represent your system for compilation in your Intel Quartus Prime software project. To finish this training, let's discuss how to incorporate your completed system design into the Intel Quartus Prime design flow. As a reminder, here is a quick review of the typical FPGA design flow. It starts with creating the design according to your required specifications, usually in a hardware description language following good RTL design practices. This can be followed optionally by an RTL simulation to test the functionality of the design. Next, synthesis turns the design into device-specific primitives, and place and route, performed by the Intel Quartus Prime fitter, selects locations in the device for those primitives and wires them together. As you've seen, Platform Designer is a front-end tool for building a system. It generates regular HDL code, so think of it as just another method for design entry in the flow. Following this flow, to incorporate a Platform Designer system, first, create the system as discussed so far. As mentioned earlier, make sure that the correct target device has been set in Platform Designer. This should already be done if the system was created from an open project, but it's still important to verify. This should not be an issue in the Pro Edition, since a Platform Designer system must be associated with a particular project when the system gets created. Next, decide what should be the top-level entity in your project and where the Platform Designer system exists in the project hierarchy. If the system itself is to be the top-level entity for the project, specify the name of the system as the top-level design entity name in the Intel Quartus Prime project. If the system will be lower in the project hierarchy, use the instantiation template discussed earlier to instantiate the system at the correct location. If the I/O pin names are to be different from the names of the signals exported from the system, you'll need to do this, essentially creating a wrapper to translate the system's exported signal names into the desired I/O pin names. Next, choose how you want the system to get generated, either manually as discussed earlier or automatically during compilation. Your choice will determine what files, if any, need to be added to the project. If you're using the Pro Edition, it does not matter which method you choose. The Intel Quartus Prime software will generate or regenerate the system as needed. No additional files need to be added to the project. However, if you're using the Standard Edition, you will need to add a file to the project, either the .qsys file or a .qip file. If you want automatic generation during compilation, add the system's .qsys file to the project. While this avoids manually generating the system every time you make a change to the .qsys file, project compilation time will be longer. If you always want to manually generate the system, do so and then add the system's Intel Quartus Prime IP or .qip file to the project as a design file. This single file, generated by Platform Designer, is a script that adds all the other generated system files to the project at once. After the system is manually generated, the .qip file is located in the synthesis subdirectory created by Platform Designer. If you make a change to the system design, you'll need to regenerate to create a new, updated .qip file. This shortens compile time, but if you forget to regenerate the system, the project will not be using the most up-to-date files. Next, constrain the project as usual. Add project constraints such as I/O assignments using tools like the Pin Planner or the Assignment Editor, design optimization settings, and .sdc timing constraint files. While the generated Platform Designer files will include .sdc files for the interconnect and some IP, you must still create a top-level .sdc file that defines clock inputs into the system as well as for PLL-generated clocks. You may also need to constrain I/O timing for components that connect directly to device I/O that do not generate their own .sdc files. Once all required constraints are created, compile the project. If at any point you need to make changes to the Platform Designer system, make the changes in Platform Designer and follow the rest of the steps in this flow. Do not edit the generated HDL directly. If you edit the generated HDL, your changes will not get back annotated into the .qsys file, and they will get overwritten the next time the system is generated. So now that you know the basics of building a system in Platform Designer, what can you do next? Here are a few suggestions. As mentioned in the introduction, Platform Designer lets you easily use and reuse IP and system designs. But what if you could create your own component that could be used in any system? Platform Designer includes the component editor, which lets you do this using your own HDL code and a simple wizard. Learn about this process in the Creating Platform Designer Components chapter in the user guide and the linked e-learning. You may also want to know how to add a processor to the system design, either the Nios 5 soft processor implemented in FPGA logic or the hard processor system, or HPS, found in Intel SoC FPGA devices. Use the linked documentation and e-learning or attend a free instructor-led training class to get started with either of these. This concludes the training. You should now understand how Platform Designer provides an easy-to-use interface for constructing embedded system designs targeting an Intel FPGA device. As you saw, the tool includes a variety of tabs and views for creating and analyzing the system. Once created, a Platform Designer system fits easily into the typical Intel Quartus Prime software design flow. Platform Designer can be thought of as just another method of design entry for your project. This concludes the second and final part of the training. If you missed the first part, you can register for Part 1 for free at the link shown here. To learn about additional resources available to help you with using Platform Designer, continue to the next slide. To learn more about Platform Designer, see the standard or pro version of the Platform Designer user guide, found with all the other Intel Quartus Prime software user guides at the link shown here. For more information about the standard interfaces supported by Platform Designer, see the Avalon and ARM-AMBA AXI interface specifications. Also, don't forget about the built-in help found in both the Intel Quartus Prime software and Platform Designer. Free self-paced e-learning is available as well. Check out the series of Advanced Platform Designer e-learnings or the additional ones listed here. You can learn details about the standard interfaces supported in Platform Designer and about the unique features found only when using Platform Designer in the Intel Quartus Prime Pro Edition. We also offer a free one-day instructor-led virtual training class that goes into detail on Platform Designer use and includes a complete lab exercise where you get the chance to build and test a system design on an Intel FPGA development kit. Intel offers many options for learning about our FPGA products and for training on their use. The Intel FPGA YouTube channel contains a number of 5-minute quick videos, along with longer, more in-depth training. The Intel FPGA training website is the place to go to learn about our recommended curriculum for every type of user and to register for a class. While there, you can register for over 300 e-learning courses, just like this one, made up of narrated slides presented in an interactive player. You can also register for one of our full-day instructor-led training classes taught by experienced training engineers, either in person or virtually over the web. All instructor-led courses have hands-on lab exercises to practice the concepts you learn. If you need further assistance, Intel FPGA provides many self-help resources. Check out the landing pages accessed from the main Intel website that are dedicated to specific FPGA technologies like high-speed interfaces and external memory. Finally, you can also view and post questions to the community forum, monitored by skilled Intel FPGA application engineers. One more thing. When you registered for this e-learning, you should have received a link to a short survey where you can provide feedback. We'd greatly appreciate it if you'd fill out that survey now. We're constantly updating and improving our training materials, and your feedback helps us create the materials that you want. Thank you for your feedback. My name is Steve, and I want to thank you for taking this training about creating a system design with Platform Designer.